We're now going to look at some stoichiometry problems for reactions that involve gases. Okay, so important thing to remember here is that when you need to figure out moles of a gaseous reactant or product, you can determine the moles from data, pressure, volume, or temperature data. So if only one reactant or product is involved in only one reactant or product involved in your reaction happens to be gaseous, then the number of moles of that reactant or product will just be equal to PV over RT. You just use your ideal gas equation. Now, if you have more than one reactant or product that's gaseous, you're going to have to use Dalton's law. Okay, so you're going to have to deal with partial pressures to get the moles of your uh, reactant or product that might be gaseous. Um, Typically, you would have enough information to figure out the total moles of gas in a reaction uh, from the change in the total moles of gas in your reaction from the change in the total pressure or the change in the total volume. So if you happen to be doing a reaction in a fixed volume container and the temperature is constant, then you can say since N is PV over RT, right? Since N is PV over RT, then if your volume and temperature are constant, then the change in the number of moles would be just V over RT times P final minus V over RT times P initial, right? So this is final moles minus initial moles. And so you can see this will just be equal to V over RT times delta P. Okay, so change in total moles will be equal to change in total pressure times V over RT. Similarly, if you're letting your volume change so that the pressure remains constant, so you're keeping your pressure and temperature constant, then the change in moles will just be change in volume times P over RT. That should be fairly straightforward to show. Okay, so let's look at an example. Let's say you have a driver's side airbag. Okay, it contains sodium azide. Typically, a driver's side airbag will have about 50 to 80 grams of sodium azide. So let's say you have 50 grams of sodium azide. To what volume will it inflate? Okay, let's say you get into an accident, the airbag deploys, the sodium azide is going to undergo these reactions right here. Okay, so to what volume will it inflate at a pressure of 1 atmosphere to 98 Kelvin, so that's typical conditions, right? If the following reactions occur, assume you have an excess of potassium nitrate. So what happens is your sodium azide will decompose into sodium and nitrogen gas. It's this nitrogen gas that causes your airbag to inflate. Then the sodium that you produce will further react with something else in your airbag, potassium nitrate. That will give you potassium oxide, sodium oxide, and even more nitrogen. Okay, so these equations are already balanced for you. So all you have to do is solve for the amount of nitrogen that you're going to get. So the strategy for solving this problem is solve for the moles of nitrogen. And then from the moles of nitrogen, you can get the volume of the airbag, which will be equal to moles of nitrogen times RT over P. Okay, we know your T and you know your P. Okay, and so the question is, how do you solve for moles of nitrogen? Well, this is a typical stoichiometry problem, right? So 50 grams of sodium azide, NaN3. Change that to moles. So sodium azide molar mass would be, let me look it up, sodium NaN3 molar mass. You can always calculate it. You should know how to calculate it. 65.00, okay, 65.01. So 65.01 grams of sodium azide for 1 mole of sodium azide. That gives you moles of sodium azide. And from that, you can calculate moles of nitrogen. So times 3 moles of N2. Okay, your balance equation says 3 moles of N2 for 2 moles of sodium azide. So 3 moles of N2, 3 moles of N2 over 2 moles of NaN3. That gives you moles of nitrogen from the first reaction. So that gives us 50 divided by 65.01 times 3 divided by 2. That's 1.154 moles of N2. 3 sig figs, so 1.15. I have 3 sig figs over here. Okay, but that's not the only source of N2. I have to figure out how much sodium can I get, and from that sodium, how much N2 can I get. All right, so the next step is to find the N2 that comes from the second reaction. So again, we start with 50 grams of sodium azide. Change that to moles. 1 mole of sodium azide, 65.01 grams of sodium azide. And then you multiply that by, change that to moles of sodium. You want to look for the sodium. And then from the moles of sodium, you can figure out how many moles of nitrogen. So according to this, 2 moles of sodium for 2 moles of sodium azide. So times 2 moles of sodium for 2 moles of sodium azide. Okay. So that cancels moles sodium azide. I now know my moles of sodium. So the sodium to nitrogen ratio right here is 1:10. 1 mole of nitrogen gas for 10 moles of sodium. Okay, so times 1 mole of nitrogen for 10 moles of sodium. Okay, so moles of sodium cancels out here. This gives you moles of nitrogen from the second reaction. We have 50 divided by 65.01. That gives you moles of sodium azide times 2 over 2. That's the same moles. So that would be moles of sodium. And then times 1 divided by 10. That gives you 0.0769 moles of N2. Okay? This is moles N2. So total moles of N2. It's 0.0769 plus 1.154. That gives you 1.23. Okay, so total N2 moles is, how much was it? 1.23 moles. And now, all I have to do is to get the volume of the nitrogen, that will be the volume of the air gas, moles of N2 times RT over P. So moles of N2 is 1.23. R is 0.08. I need some room here. Okay, so 1.23 moles times R, which is 0.08206 liter atmosphere per mole Kelvin, and temperature is 298 Kelvin, divided by our pressure of 1 atmosphere. So atmosphere cancels out, Kelvin cancels out, mole cancels out. That gives you the answer in liters. So you have 1.23 times 0.08206 times 298 divided by 1 is 30.07 liters. So that's 30.1 liters.